Hey stat students, this is the last lessons video for Unit 11, Lesson 3, Inference about Slope. We've already created confidence intervals. We talked about the sampling distribution of sample slopes. Now we want to do a hypothesis test for slope. So instead of just saying, well, I think that the population regression line slope is between these two values for the confidence interval, we can say, well, somebody says it's this, let's test to see if it is. So we're going to do a significance test to determine whether a specified value for beta, the population regression slope, is plausible. So the null hypothesis will have the general form of the null hypothesis. The null hypothesis will be that the population slope, beta, is equal to some number, and that's b sub 0. So this is the value for the slope that we're going to test. Pretty much always we're going to set it as 0. It's possible to do other things. We're going to be testing 0. So to do this, we always use our familiar formula for our standardized test statistic. So the statistic is our best guess at the parameter value. So if I would like to know the population slope, I'm going to guess my sample slope. The parameter is what we're assuming to be true. So this is the population slope from the null hypothesis. And then we'll divide by the standard error of the statistic, which is b, the sample slope. Now, because we will almost always be using this as 0, this is pretty nice. This is just going to be b minus 0 over some number, which means just b divided by the standard error of that statistic. So to find our p-value, we will use a t-distribution, and we will be using n minus 2 degrees of freedom. So if the sample data suggests there's a linear relationship, we can determine whether this is just by chance or if there's an actual linear association for the population values of x and y. So by performing this test, what was I saying? Sorry, I got distracted. By performing a test of the null hypothesis, beta equals 0, a regression line with a slope of 0, we're saying it's horizontal, meaning the average y is not changing at all when x changes. That's what we're saying. Null hypothesis, assume that the relationship is a horizontal line. There's no change at all. The linear regression that we could make is not any better for predicting y than the average response variable y bar. So basically, there's nothing linear about it. You might as well just guess y bar instead of using the linear regression. We will be using computer software. We'll come back to it in a second, but it's reporting p-value for a two-sided test, so we'll have to be careful about that. But we will be doing one-sided tests in a proper direction. So for example, infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. So they wanted to explore this relationship between crying infants and their IQ test scores later. They snapped a rubber band on the sole of the feet of infants, which seems a little cruel, but they recorded their crying times, measured the intensity, and then checked their IQ later. Now they did this for 38 infants. We have the data here. And then there's a computer output for the least squared regression analysis. So they created a scatter plot, fit it to the regression line. We looked at the residuals. They took those residuals, put them in a histogram, and then also gave us the regression analysis output. So we are going to be going through our process, the 4-step process for a hypothesis test. So I'm just going to state that I would like to know, I don't know why I'm using purple, sorry. We're going to be testing beta equals 0. We're going to assume that's true until proven otherwise. And we're going to contrast it against, not just that it's not 0, if I read carefully, we're testing a positive linear relationship. So not only is the sample regression line's slope positive, but we think maybe that the population might be positive too. That's what I'm going to test. I'm going to test that beta is greater than 0. And I have to define that beta, is the slope of the regression line. We're relating these y IQ scores with the x count of crying in these infants. There is no significance level stated, so I'm just going to use alpha being 0.05. Remember, you can choose whatever you want if it's not stated, as long as you say that you're going to use that. We do have to test our conditions before I finish my plan. I should write that I'm about to do a t-test for the slope. we still need to check those liner conditions for inference. So I need to look at these graphs. The L part of liner is linearity. So when I look at this, it doesn't just look like a scatter plot. Now, it isn't very close linear relationship, but it does seem overall to be increasing. It seems to have some linear pattern. So I'm going to note that the scatter plot shows a linear relationship between my x and y variables. And when I look at the residuals, there's not a curved pattern here. So there's not anything left over that could be explaining things. It's probably linear then is what that means. So that's the L of liner. I is independent. Since we are selecting infants from the greater population, I should check my 10% condition. It said, how many did we have here? 38 infants. And you can assume that that's less than 10% of all infants, so we're good with independence. And then we next need to check for normality. So if I look at the histogram of our residuals, it isn't perfectly symmetric, maybe slightly skewed right, possibly maybe. But the key thing here is there's not dramatic skewedness, there are no outliers. So because of that, we can assume that we have normality. For the equal standard deviation, the E part of liner, what we see here is, for the most part, some similarity. Now, it ever so slightly starts shrinking in-ish, but it's not like dramatic enough where there's all these dots and then teeny tiny little, that's not really what it looks like. So because it's kind of close enough, we're just going to say that it shows a fairly equal amount of scatter around this horizontal line for all x values. It's good enough. And then R is always random. It said it was a random sample of infants. So again, I already had that all written up because you didn't need to watch me write all that out when that was in the last video. I've just checked all my conditions, so I can go ahead and do this. Where am I at? So I have 36 degrees of freedom because I took my sample size of 38 and subtracted 2. Our test statistic, we said you need to take your statistic minus the null hypothesis value divided by the standard error of the statistic. So B is the sample slope. If I go to this output here, remember we want to look in the coefficient column, and one of them is going to be a constant, one of them is going to be one of our variables. Now if you look over, the cry count is the x variable. So when it says that the cry count's coefficient is 0.487, that means the coefficient of the variable x is 0.487. The constant value is 8.93. Oh, I'm in the wrong column. The one that says just plain coefficient is what I should have been looking at. But I do still want to call the cry count. So the coefficient of our x variable is 1.4929. And the coefficient that's just a constant value is 91.268. So back in Unit 3 when we did this, we're finding our sample regression equation is what this is. So this is our y hat equals a plus bx, where this is our y-intercept, and that's our slope. So this is our sample slope. So 1.4929 is what I put in the numerator here. We're gonna, 4929, we're gonna subtract b naught, which is what we're testing b, we're assuming to be true in our null hypothesis. So I'm gonna subtract 0. And I'm gonna divide by the standard error of the slope, which is in our equation here. There is a formula for it. It's always going to be up here. So right to the right of this value is the standard error of that variable. I forgot what I just was doing. 487. So when I take 1.4929 divided by 0.487, I'm getting 3.07-ish. Now that's a t test statistic, so I need to think of my t distribution with 36 degrees of freedom. So if I think of this value, and it was a right-tailed test because our alternative hypothesis had a greater than symbol on it. So this would be the area corresponding to our p-value. We could find that p-value by doing a TCDF, saying I would like to go from the lowest value of 3.07, never stopping on the upper end, but with 36 degrees of freedom. So when I put that in my calculator, I'm getting a very small number. So my p-value is 0.0020. So it's small. It's definitely going to be smaller than any value of alpha I would have picked. So because 0.0020 is less than our stated level of significance, we're basically saying we were assuming the null hypothesis is true. We got this value. It is really unusual. So because that's the case, this is the probability of getting that test statistic or something even higher, we're going to reject the null because it's more likely that that was just not a true thing to be assuming in the start. So we do have convincing evidence of our alternative, that's hard to say. So there is convincing evidence that there's a positive linear relationship between these x and y values, between the crying peaks and the IQ scores in the population of infants. So not really that different. There's one new formula here to calculate, but your calculator can do this for you if you would be willing to put in the data into your calculator. Now, 38 data values is probably not the best use of your time when that is not a difficult formula to create on your own. But if you were to take the time, like I did, to put in all your x values that were given, all your y values were given. If you scroll stat tests, when we found our linear regression t interval, so this was the interval for our population slope value, right above it is the linear regression t test. So I'm saying my x values are in L1, my y's are in L2. I'm testing for a positive relationship. So please calculate that for me. It's just restating what I was testing. This is related to our correlation coefficient, but we're not going to get into that. I'm getting the same test statistic that we calculated by hand, the same p-value that we used TCDF for, tells me my degrees of freedom. Honestly, it reiterates the same values that were in that output in the first place. But this is the key thing here. We can go ahead and say, oh, because this p-value is so small, we're going to reject the null, and there's evidence for the alternative. So that's a summary of what we just did that's in your notes of how to go through and find those if I went too quick for you. There is another example that's on here that I would suggest that you try on your own. I feel like there's something I was going to say about this. Oh, that's the other thing I was going to say about this. When you look at this, let me remember where I'm looking. If you look up here at the p-value, the p-value for, remember we said this is our y-intercept row, this is our slope row. If you go down to the end of this, you're going to find a p-value for the slope, but it's not the same number that's given to us. So the thing that I kind of breezed over and said I'd come back to is that computer software gives you information for a two-sided test. So if you just need a one-sided test, you're going to divide that p-value output by 2. So if it's telling me my p-value is 0.004 for a one-sided test, it would be half of that, which, wouldn't you know, 0.004 divided by 2 is the p-value that we found by hand. So even if you don't want to go through all of this work and it just spits it out, the regression information here, we can look here. The constant again is your y-intercept value information. The row, this is talking about the row of where somebody sits in class. So we'd have the sample slope value, the standard error of that statistic, and then this p-value is again for a two-tailed test. when you, assuming you are going to actually try this on your own, we are supposed to be testing for a negative linear relationship. Since we want it to be negative, you should be testing a left-tailed test. So you will not use that whole p-value. You need to take half of it. They're giving you the two-tailed test data. So when I did this here, I just noted I need half of that p-value. So when you're working through it on your own, you can make note of that. Yeah, I'll just stick with that. So again, that should be everything. So theoretically, you're doing this the week that it came out. I know that is not true for a bunch of you, but there's at least one of you that's been doing a great job of keeping up with everything. Everybody else, do the best that you can to be done by May 8th, because that's when seniors are done and you can finally stop pretending like you are able to teach yourself perfectly at home, and at least you can try to have a somewhat normal summer. So do your best to finish all this stuff up to the best of your abilities. Email me lots of questions. I will attempt to respond back in a timely manner. I've apologized to multiple of you guys, but still, sorry that Khan Academy sucks. I knew it wasn't great for my end trying to tell what you guys could see, but I had no idea what a mess it makes of assigning things. I had assumed, apparently incorrectly, that when I assign things, it puts it in the